Assalamu alaikum. This is the continuation of lecture number 3. So the content we are going to study today, the surface tension problem that we have, the derivation we did last time, the capillary and capillary effect, compressibility of fluid. Then we will do up to some extent chapter number 2. We will start a new chapter, that is a fluid static. And in this fluid static we will see what is fluid static, the pressure force and the pressure at a point that we will study. So now let's move on to the previous lecture. We left the previous lecture here. We derived the equation for the water bubble and for the soap bubble. Okay, how the soap bubble can be survive, how the shape and size of the soap bubble and the water droplets can be controlled. Okay, so now let's move on to a problem. So there is a problem: find the surface tension in a soap bubble of a 40 mm diameter when the inside pressure is 2.5 Newton per meter square above atmospheric pressure. Okay, so here the soap bubble is given and the pressure difference, because the inside pressure is above atmospheric pressure. So that means this is delta P, which is given above atmospheric pressure. So let's see. So in case of a soap bubble, we derive an equation. So this is the equation for the soap bubble we derive, that is 4S over R. Okay, so this is the equation. P is equals to 4S over 4 sigma over R, that mass into R. So if you are using a diameter, so what will happen? Diameter is equal, R is equals to D by 2. So it will move on to 8 sigma S over R. So here is the equation. So because here P is equals to 4 sigma over R, so R is equals to D by 2. So when it will come to this, so pressure X outside is given for a soap bubble using, and diameter is given. So everything is known. So we can calculate the surface tension of the soap bubble, which is equals to 0.0125 Newton per meter. So it's so simple. Okay, if this bubble want to survive, the surface tension of the fluid must be 0.0125. Okay, so now let's move on to the capillary effect. What is the capillary and capillary effect? So the rise or fall of a liquid in a small diameter tube inserted into the liquid. So whenever we insert a small diameter, this is very important, a small diameter tube, when we insert in a liquid, we can observe the fall or rise of a liquid in the capillary tube. Such rise or fall is called the capillary effect. So what is capillaries? Capillaries, such a narrow tubes or confined flow channels. Okay, the capillary effect, the application of the capillary effect is partly responsible for the rise of water to the top of a tall trees. So meniscus, what is the meniscus? Meniscus is basically the curve. This is a upward curve, and this is the bottom curve. So this is called the bottom lower meniscus, and this is called the upper meniscus. This happen because of the wetting of the fluid. Okay, this happen because of if the fluid is wetting, adhesive force is more, so that's why the surface is sticking with the fluid and it is going up. So the fluid going to be more wetting, or it is also called a contact angle. The contact angle will be less, the liquid will be more wetting. So if the contact angle is more, the liquid will be non-wetting, is the less wetting. So just like a mercury, in the mercury, the cohesive force between the molecule of the mercury is more. Because of that, the adhesive force between the mercury and the glass tube is, or the container is, less. Because of that, the contact angle is more. The contact angle is more, the fluid going to be non-wetting. Okay, so let's move on to the next slide. So this is, you can see the two capillary tubes, one in water and one in the mercury. So if the molecule of a liquid have a greater adhesion, just like as shown here, if the molecule of a liquid have a greater adhesion than cohesion, then it wet the solid surface. Here it's wetting the solid surface. The contact angle with the solid surface, and if you make a tangent, it is very less. Then it wet the solid surface and result in capillary rise. So here there is a capillary rise. It is capillary rise. Water example, just like water. Water in glass tube. The angle of contact in case of capillary rise is less than 90 degrees. So if you make a tangent here, you can say, or you can say in the previous slide, this is the angle of contact with the water and the glass is less than the 90 degrees. So because of that there is a capillary rise, because there is a small bonding between the liquid and the solid surface. Now cohesive force between the fluid molecules, or the cohesion is predominant, then what will happen? The liquid will not wet the solid surface, as we can see here. This result in capillary falls. So this is, we can see a capillary falls here. H is less than, H is greater than 0 and H is less than 0, it is going down. So we can see the capillary falls. Just like this is the mercury in glass tube, the angle of contact in this case is greater than 90 degrees. So if you make a tangent here like this, as in the previous slide, if you make a tangent like this, so this angle of contact is more than 90 degree. Now there is a question that how we can neglect the capillary effect. How we can do that? We can neglect the capillary effect only by increasing the diameter of the tube, because here you can see this is the capillary rise, is indicating with the H, and it is directly proportional to the, it is inversely proportional to the radius of the capillary tube. If you increase the radius of the if you increase the diameter or radius of the capillary tube, what will happen? The capillary rise will fall, because these are inversely proportional. Now let's see how we can drive this equation. So here you can see we have a container and there is a capillary tube inserted in the fluid, and here is the fluid which is lifted due to the capillary effect, which is height. So how we can calculate that? If we insert a capillary tube of a particular radius, that is r, so what would be the capillary rise? How we can calculate? Let's see. So the capillary rise is indicating with the H. The fluid lifted due to the capillary effect, it has a particular weight, that is basically the W. Okay, and this weight is held due to the surface tension force, okay, which is acting at the circumference of the inside tube. We are neglecting the thickness of the tube, okay, and small r is the radius, is the curvature of the meniscus, is the radius of the meniscus, because meniscus is in a curved shape, so it has a meniscus, that is r, and the angle between the solid surface and the tangent is phi. So there is the only force which is balancing the weight of the lifted fluid, that is the surface tension force. So let's see how they are balanced. So sigma force is equals to 0. So first we can see what is the total surface tension force and what is the total weight force of the water. So rise of liquid, that is weight, is equals to sigma cos phi into length, because sigma is equals to sigma into what is basically the surface tension force. So force is equals to sigma is equals to force per unit length. So if you multiplied sigma with the length, you will get the force. So here this is the direction of the surface tension. So the weight of the fluid is acting vertically downward, so that means only a component of this force will balance of it. So what is the component of it? That is the sigma cos phi. sigma cos phi multiplied by the length, which is the surface tension. There is only one free surface, and what is the length where the surface tension force is acting? That is basically the circumference of the tube here. So what is the circumference of the tube? Is 2 pi r. Okay, that means sigma cos phi multiplied by 2 pi r is give you the surface tension force. And how about the weight of the liquid? What is the total weight of the liquid? Total weight of the liquid is equals to density of the fluid. Okay, so what is the weight? Weight is equals to mg. So g is here. So mass of the fluid is equal to rho into v. So rho is the density of water, and what is v? Is the volume of the fluid. What is the volume of the fluid? The height h multiplied by the area. What is the area? Area is pi r square. So that means height h into pi r square. So here pi and pi, 1 r and r is going to be cancelled. So finally it will end up with h is equals to sigma cos phi mu into r into g. Okay, so for the water the phi is equals to 0, and for the mercury the phi is 128 degrees centigrade. If it is not given in the question, in the problem, so you can assume yourself. Okay, so here is the derivation of this equation. So fine, let's move on a numerical. A 0.6 mm diameter glass tube is inserted into a water of 20 degree centigrade, because this is very important, because surface tension is a function of temperature, so it must be mentioned. In a cup, determine the capillary rise of water in the tube. So we have to find out the capillary rise in the 0.6 mm diameter tube. So we know the equation of this. So let's see what are the things are known and what are unknown. So we know 20 degrees centigrade. Here is the figure is given. So 2 sigma s cos phi mu g into rho g into r. So what other things are given? Diameter is given, that means r is given. Okay, so this is what else is given? There is a water. For the water we know phi is 0 degrees centigrade, which is here. What else? G is 9.8 if it is SI unit, and rho at 20 degrees centigrade that we can see is 1000 kg per meter cube. And what else is given? The sigma s. Sigma s we can calculate for the water from the table 2-4. Okay, from the fluid properties we can calculate. In the previous lecture I have shown you the surface tension of different fluids in different temperature, that you can calculate the surface tension of fluid at 20 degrees centigrade and you can insert it here. And when you end up, then we can see 5 centimeter is the fluid will rise up to 5 centimeter. Okay, so this is end of the capillary effect, capillaries and capillaries effect. We have observed the now the compressibility of fluids. We have observed in solids when we applied pressure, the solid compresses. Just like here, if we P1 is the pressure, the atmospheric pressure, if you apply the more pressure on it, the volume of the size decreases. Same thing we can experience in fluid. The fluid usually expands as they are heated or depressurized. Okay, they expands, and contracts as they are cooled and pressurized. But the amount of volume changes in different for different fluids, because the fluids have a different properties, so they expand differently or they contract differently, and we need to define properties that relate volume changes to the change in pressure and change in temperature. So we need a term that can express the change in volume due to change in pressure or change in volume due to change in temperature. So both temperature and pressure we cannot vary at the same time. So here we have two different terminologies: the bulk modulus of elasticity, that is K, and the coefficient of volume expansion, beta. The bulk modulus of elasticity, the change in volume due to change in pressure at constant temperature, okay, and the volume expansion is the change in volume due to change in temperature at constant pressure. So let's see the coefficient of compressibility, and it is also called a bulk modulus. It is indicating with the K. So what is the bulk modulus and what is the coefficient of compressibility? It is basically the fractional, the coefficient of compressibility represents the change in pressure. This is the change in pressure correspond to the fractional change in volume. So this is basically the fractional change. Delta V over V is the fractional change at constant temperature. Okay, so here there is a negative sign. It's indicating that if you increase the pressure, the volume will decrease. Okay, so that means the one thing is increasing and one thing is decreasing. So this is the negative sign is indicating. And same thing we can express in terms of density. Okay, so the change in pressure correspond to the fractional change in density of the fluid while the temperature remain constant. So we can define the bulk modulus or coefficient of compressibility in terms of density also. So this change in pressure or this increase in pressure correspond to the fractional change in density. Here there is a positive sign. If you increase the pressure, what will happen? The density will also increase. The change in density will also increase. That's why it's a positive sign. So what is the coefficient of compressibility of a truly incompressible substance? If a substance is incompressible, so what would be the coefficient of compressibility? A large value of K indicates that the large change in pressure is needed. Okay, a large value of K indicate that a large change in pressure is needed to cause a small fractional change in volume, and thus a fluid with a large K is essentially incompressible. If the value of K is more, that means fluid is incompressible regardless how much pressure you are putting on. If K is less, that means fluid is compressible. If you increase the pressure, you will get the density increase. Okay, so now let's move on to the for the ideal gas. For an ideal gas, if you want to calculate the density change, or if you want to calculate the density change due to the increase in pressure, then how would you do that for the ideal gas? So this is the equation basically which relates temperature, pressure and density. So here it is, P is equals to rho RT. So P is equals to rho. If you consider T is a constant and R is a constant, if you take the derivative, so this is the change delta P over delta P is equals to delta rho is equals to RT. R and T is constant. So delta P over delta rho is equals to, at constant temperature, is equals to R into T. So here delta P over delta rho at constant temperature is equals to P over rho. If we can see from here, okay, we can see from here. So this is equal to the, so compare these two equations, that one is delta P over delta rho at constant temperature is equals to RT, and here that is delta K divided by rho delta P over delta P at T. So if you compare these two terms, so you will end up with so now replace this RT, because RT is equals to del P over del rho at constant temperature. So replace this RT with this term. So this term is equals to P, then P will be equal to rho into del P slash del rho at constant temperature. So rho del P over del rho will be equal to rho del P over del rho at constant temperature will be equal to K. So that means K of ideal gas, the compressibility of ideal gas will be equal to the applied pressure. So we can say that the coefficient of compressibility of an ideal gas is equal to its absolute pressure, and the coefficient of compressibility of the gas increases with the increase in pressure. As the pressure will increase, the coefficient of compressibility will increase. So further, here we can write down del P over del rho and del P over del P. We can write down. Okay, so this state that the percent increase of density of an ideal gas during isothermal compression is equal to the percent increase in pressure. Okay, so there is another term, that is alpha, which is the inverse of the compressibility. What it is states that the isothermal compressibility of a fluid represents the fractional change in volume or density correspond to the unit change in pressure. So now next move on to the now the coefficient of volume expansion. We are familiar with this term. To quantify the quantify of these effects, we need a property that represents the variation of the density of a fluid with the temperature at a constant pressure. If we increase the temperature, then how the density and volume changes at a constant pressure. We need a term that is basically called the volume expansion. So the coefficient of volume expansion can be expressed as the fractional change in volume correspond to the change in temperature represents with the coefficient of volume expansion beta. So here you see the term is positive, both the terms are positive. As the temperature increases, the change in volume increases. Here there is a negative sign appears. That means the change in density. As the temperature increases, the fractional change in density decreases, the density of the gas decreases. So this is the indication of the change in density or volume due to change in temperature with respect to pressure. So okay, here the volumetric expansion beta, the value of beta indicates a large value of beta for a fluid means a large change in density with temperature, and the product of beta delta T represents the fraction of volume change of a fluid that correspond to the temperature change of T at constant pressure. That means if you have a large value of beta, that means you can change the density by increasing the big change of temperature. That means the change in density or change in volume is available with change in temperature at constant pressure. The value of volumetric expansion for an ideal gas can be calculated as 1 over T. So this is the value of volumetric expansion of the. You can drive it as we drive the coefficient of compressibility of an ideal gas at constant pressure. So you can at the constant temperature. Now you can calculate for the and just check whether the volumetric expansion of ideal gas comes 1 over T at constant pressure. Here in the picture you can see there is a container available, or the piston container available. There is a gas or the liquid or whatever the fluid is available at 100 kilopascal. 1 kilogram is the weight in 20 degrees centigrade. Okay, so here the substance with a large beta. Why? Because delta V over delta T at constant pressure, this is very big. That means there is a possibility to increase. Here when we heat it up, okay, and we have to maintain the constant pressure 100, then we allow it to expand, okay, to maintain the constant pressure. Okay, so we see there is a big change in it because of the large value of beta. Here the same case, but the small value of beta is indicating the less change, and it indicates the big change. The coefficient of volume expansion is a measure of a change in volume of a substance with temperature at constant pressure. So K and beta are basically the two terms which indicates the change in volume at constant pressure, at constant change. The K indicates, that is a compressibility coefficient. The K indicates the change in volume with respect to change in pressure at constant temperature, while beta indicates the change in volume due to change in temperature at constant pressure. If the value of K is big, that means the fluid is incompressible. If the value of K is small, that means the fluid is compressible at constant temperature. If the value of beta is large, that means the fluid is compressible at constant pressure. If the value of beta is small, that means fluid is incompressible at constant pressure. So now we are going to start the next chapter, that is fluid static. Fluid static. So what is fluid static? Fluid static is the part of fluid mechanics that deals with no relative motion between the fluid particles. Typically, the situation of fluid static includes two situations. Number one, the fluid is at rest. Fluid at rest can only withstand with normal pressure or stress. In that case, we can see only the normal force is acting on the surface when the fluid is at rest. There is no irregular force are acting on it. Next, the fluid moving like a rigid body. In rigid body motion, all particles are in combined translation and rotation, and there is no relative motion between particles. So here we can see the case where there is a motion, but there is no relative motion between the fluid particles. There is a relative motion between the fluid particles and the surrounding. Since there is no relative motion between the fluid particles, that means there is no shear stress. If there is no shear stress, that means there is no deformation. So this is the second case that we will discuss in the later part. So first of all, we will discuss in detail the fluid is at rest. So let's move on to the fluid is at rest. The fluid is at rest is all about pressure. So here are the rules to remember and to study. So what we are going to study in fluid is at rest. Number one, the pressure at any point in a fluid is same in all direction in a same plane and is transmitted through static fluids without loss of energy or pressure. This is called Pascal principle. So here you can see the pressure at any point, that we will prove it and we will see, and in all direction is same and it is transmitted through the static fluids. So next, the pressure at the wall of any vessel is perpendicular to the wall. Here you can see an irregular surface which is holding a fluid. So if this is our surface, consider this is the surface. So we can see the pressure distribution on it. The pressure distribution on it is uniform, and this is the meaning the pressure at the wall of any vessel is perpendicular to the wall. So all the pressures are perpendicular to the wall. Here you can see the pressure is perpendicular to the wall. Here you can see the pressure is perpendicular to the irregular surface. So this is the situation कि always when the fluid is at rest, the forces acting perpendicular to the surface. The number 3, the pressure due to depth is same at any horizontal level of connected fluid. So this is the continuous fluid. There is no break on it. That means let's consider this surface. This is the horizontal surface. You can see the pressure distribution. The pressure distribution is throughout same in the horizontal surface. Next, fluid and pressure increases with the depth, and you can see the depth from B to C, the depth of the fluid is increasing. So you can see the pressure profile. As the depth is increasing, the pressure profile is also increasing. So this is the point number 3 that we have to remember, and this we will prove how to calculate, how to prove that the pressure at a point is same in all the pressure at a point, the pressure acting at a point is same in all direction, and also what is the magnitude and position of the force acting on a different depth of the fluid, that we will also learn. So here in fluid static mainly we talk about the pressure. So let's see what is the pressure. So what is the pressure? Pressure, a normal force exerted by a fluid per unit area. So here you can see the pressure is equals to force per unit area. If you see the pressure is if you say pressure equal to force per unit area, this is not the appropriate definition. The pressure is the normal force per unit area, because if the force is not normal, and you are suppose if there is a force which is acting with a certain angle and you use that force straight away in your calculation, that means the pressure you have calculated, it's wrong. To calculate the pressure you have to take only the component of force that is perpendicular to the surface or perpendicular to the area. As it is, you see this force is perpendicular to the area A, so we can say that the pressure is equals to force per unit area. So the pressure, the unit of the pressure we measure in Newton per meter square, and that is also called Pascal. So because force unit is Newton in SI system and area is meter square in SI system, so Newton per meter square is also called 1 Pascal. So we can see here the pressure is depending on two things, force and area. The pressure is inversely proportional to area and directly proportional to force. If you are increasing the force by keeping the area constant, the pressure will increase. If you increasing the area by keeping the force constant, the pressure will decrease, okay, because the force will distributed in more areas. If you are decreasing the area by keeping the force constant, the pressure will increase. Same here, you can see the area is constant and we are increasing the force. Weight is a force, okay. For a skinny person, we have a 70 kilogram into 9.8, so we got a force and divided by this area, so we got the pressure 20 kilopascal. And if we double the weight, what will happen? The pressure is going to be double. So this is the effect of force and area on the pressure. So what next? Now we measure the pressure in different units, and all of the units which is mentioning here is SI unit, and they have a conversion. 1 bar is equals to 10 raised to power 5 Pascal, megapascal, kilopascal, and 1 atmospheric pressure. So what is basically the atmospheric pressure? Atmospheric pressure is basically the pressure exerted by the atmosphere. So 1 atmospheric pressure, we normally 100 1.325 kilopascal. That means this is equal to 1 atmospheric pressure at sea level. If you are standing here at this point, okay, lower altitude, that means you have more air on your head. Okay, so pressure exerted by the air on your head is more, so you have a more pressure at sea level. But if you go up on the hills, on the mountain, on the high mountains, so you are bearing a less air pressure. So as you go up, the pressure will decrease. So the higher altitude have a lower pressure, the lower altitude have a higher pressure. So let's move on. We have a different type of pressure. The atmospheric pressure, the pressure exerted by our atmosphere. Absolute pressure. To measure any pressure, we need a reference point. So any pressure we measure from that reference point is called absolute pressure. So what is our reference? What is our reference point? Consider our Earth is surrounded with the air. Okay, and the pressure due to those air, we call it atmospheric pressure. And after the air, we consider there is a space. In the space, we consider there is no air, there is no gases, it's a complete vacuum. So that vacuum we consider as a zero pressure and as a reference point. Next is the gauge pressure. Gauge pressure is the difference between the absolute pressure and the local atmospheric pressure. So most pressure measuring devices are calibrated to zero in the atmosphere, and so they indicate gauge pressure. The pressure we measure in the compressor, okay, when we fill the compressor with the air, so the gauge what indicates is a gauge pressure. Okay, it is the gauge pressure. What is the gauge pressure? Okay, and then there is a vacuum pressure. Vacuum, meaning the pressure below the atmospheric pressure is called atmospheric pressure. Now is the vacuum pressure. So here is the chart that will explain how we can measure the gauge pressure and vacuum pressure. This is our absolute zero. Any pressure measured from this reference point is called absolute pressure. Any pressure measured from this reference point is called gauge pressure or vacuum pressure. So here you can see the gauge pressure is equal to absolute pressure minus atmospheric pressure. Vacuum pressure, what is vacuum pressure? When the pressure is below atmospheric pressure is called vacuum pressure. So atmospheric pressure minus absolute pressure is called vacuum pressure. So let's see a problem. A vacuum gauge connected to a chamber reads 40 kilogram Pascal. Okay, so we have a vacuum pressure that is 40 vacuum gauge. That is a gauge. Okay, at a location where the atmospheric pressure is 100 kilopascal. Okay, so determine the absolute pressure in the chamber. Okay, so the absolute pressure is what is the vacuum pressure? Vacuum pressure is equal to, as we have seen, the vacuum pressure is equals to P atmosphere minus P absolute. If you want to find out the absolute pressure, so take the absolute this side and vacuum this side. So here 100 kilopascal minus 40 kilopascal will gives you the absolute pressure. So now the fluid forces. Okay, in fluid mechanics we consider forces upon fluid elements. It is necessary to discuss the type of force that could act on the fluid element. These forces could be divided into two categories. Okay, in the fluid, when we will study the fluids, we will study two types of forces. One is the surface force and other is the body force. So just like we study the pressure force, so here is the surface force and the body force. So what is the body force? Such as gravity that acts throughout the entire body of the element and are proportional to the volume of the body, and also electrical and magnetic forces which will not be considered in the course. So here you see, if basically the body force acts throughout this volume, but when you talk about this only, this is small element. So what is the body force of this small element? That means the mass of the body, okay, the mass of the body, and the so the weight of the body is basically give you the body force. So what is the weight of this fluid element? That is equal to the weight density into volume. Okay, the weight density into volume, if you multiply with that, you will got the body force, and the body force acts throughout the object, because the gravitational force is acting here, here, here on every single particle. Okay, so if you want the body force of the whole is just take the volume of it and the gravitational acceleration and the density of it. Okay, surface force always acting on the surface, on this surface, on this surface, on this surface, on this surface. It is always depending on the surface. We do not talk about the whole body, okay, such as the pressure force. So if you are considering this object, that means the pressure is only acting here, the pressure is only acting on this surface, the pressure is only acting on this surface. So such forces are called the surface force. So now remaining topic we will talk in the next lecture.